Okay, in this video I'd like to talk a little bit about the concept of reaction mechanisms and things called elementary steps. Now, you may have heard of the term reaction mechanism before, but let me just break it down in terms of what it actually means. Whenever you talk about a mechanism for a reaction, you're talking about a series of steps that overall reaction goes through. So for example, let's say we have this overall reaction right here. 2NO plus O2 goes to 2NO2. Now, theoretically, this could go through any one of a very large number of different mechanisms. The mechanism being the exact order with which these molecules react to give the product. Now, it turns out that the experimentally determined rate law, just like determination of rate law that we've seen before, the rate law determined by experiment comes out to be this. So second order with respect to NO and first order with respect to O2. And based on that, several different possible mechanisms can be postulated. Alright? And this here is an example of a potential two-step mechanism. Okay? So whenever you see something like this, you won't be expected to come up with a mechanism yourself. Not a complete mechanism like this anyway. You're going to be asked to actually see if you can understand what's going on here and basically see, does this mechanism fit this rate law? And there's several steps to doing that. There is one thing that you've got to make sure you are very careful about when we talk about mechanisms that have more than one step. In this case, we have our two-step mechanism. The issue is that because there's more than one step, the issue of the rate of those reactions then becomes an issue. Because as we've seen before, the slowest step in a reaction, the so-called rate determining step, is the one that determines the overall rate of the reaction. And that's fine if that slow step is the first one, because even if you've got 10 fast reactions after it, they all will be dependent on products from that first slow reaction, so that determines the rate. So the rate law for a particular reaction is always going to come from that particular step. And this is where I wanted to talk a little bit about the concept of elementary steps. Alright? Elementary steps are the single steps in a mechanism that go towards forming a product. And the thing that distinguishes, for example, reaction number 1 from the overall reaction here is that we've seen before you cannot take an overall reaction and figure out the rate law from the coefficients in that reaction. It turns out here they happen to work out, but that's just the way it turns out. That's just coincidence. For an elementary step, the issue is actually a little bit different. Because it is one single step, and here this is more than one step, for that reaction that is one single step, you actually can derive the rate law from that balanced equation. Okay, so the first key thing to understand about elementary steps is that you can generate the rate law directly from the balanced equation and use the coefficients as exponents. Okay, so if we were just to look at this reaction number 2 here, this is a single step, just as this is a single step. So according to what we just said, if this is indeed an elementary step, and we can assume that it is, then the rate law for that is going to be equal to rate equals k. Because I have two separate steps here, I'm going to label my k's. Alright, k sub 2. And then I introduce the concentrations of my two starter materials, my two reactants. Okay. So I've got my concentration of my O2, NO2, my N2O2, and the concentration of my O2. I don't have to worry about x and y as exponents here because both the coefficients are 1, and this is an elementary step, so the rate law is actually exactly this. Now the problem that we get to here is that N2O2 was not a starting material, so we can't measure its concentration. Because it's produced in the first reaction, we've got to somehow take this into account. And notice that this first step, this is essentially an equilibrium. If you think what happens if you have a first step that's very, 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 very fast, and a second step that's very, 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 very slow, so when this stuff forms, it's going to be waiting around for ages and ages until it can react with the oxygen to form this product. If it's waiting around long enough, eventually it'll say bollocks to this and it'll go back to the starting materials. And that's what sets up this equilibrium here. So we have NO, we have the nitric oxide forming the N2O2, and eventually that will flip back and forth, so we have that equilibrium set up. Okay. Now we have to figure out, is there a way for us to write out the rate law for this reaction? Well, actually, yes, there is. It's very simple. For this reaction from NO to N2O2, it's just, I'm just going to say K sub 1, and then we've got NO here. But that coefficient here is 2, so the exponent here is going to be 2 as well. Okay. But because this is an equilibrium, we can also say the opposite is true. And we can say the opposite, not the opposite is true. We can write out a rate law for the opposite, the reverse reaction, which would be very similar to the first one, except it will be rate equals K minus 1, because I'm going in the opposite direction, and then the concentration of my N2O2. Okay. And what would the exponent here be? Well, if the coefficient here is 1, the exponent is 1 as well. Alright? So, you can see that because these are elementary steps, we can determine the rate laws from them. But remember, the original question was, is this rate law valid for this reaction? And we haven't really got anywhere yet. There's a bunch of stuff here we don't particularly know what to do with. But here's what we have to understand. We said before that step number 2 was the slow step in the reaction. So therefore the rate law is this. And you can definitely see that this rate law is not the same as this one. They both have O2 in it, but that's where the similarity ends. So we have to find a way of taking out this N2O2 and replacing it with something else. Because like I said before, we cannot measure the concentration of this N2O2 because it's not an starting material. In fact, if you think about it for a minute about what the name of a species is that is produced in the first reaction and used up in the second, so it's there at it's not there at the start of the reaction, it's not there at the end either. This is called an intermediate. Alright? An intermediate. And being able to recognize intermediates is important. So intermediates are present or formed in one reaction and they're used up in another, and they're not present overall. In fact, if we were to add up the overall reaction here, we just add what's present on each side and then cancel out whatever we can. The only thing we can actually cancel is the N2O2. So what we get is 2NO plus O2 goes to 2NO2. Alright? Now, this is one of the first 3 criteria that we want to make sure is true. If the 2 steps add up together to give the overall reaction, then that is good. That's one of our criteria that we have to fit. However, there are issues with the rate law, so we've got to see what we can do about that. So we're going back to where we were before. Because the N2O2 is an intermediate, we cannot have it in the rate law because we can't measure its concentration. So we've got to replace it. So therefore we need some sort of representation that involves N2O2 that we can then relate to something else. And that's where we take into account the fact this is an equilibrium. The step forwards has exactly the same rate as the step backwards, so essentially all this is equal to all of this. So what we can say is K1 times the concentration of NO squared is the same as K to the negative 1 times the concentration of N2O2. And then what I can do is I can just take the N2O2 and put it by itself. And then that gives me, it's going to give me something that looks kind of funky. I take K1 over here, and what that then becomes is K1 divided by K negative 1 times NO squared. So whether you realize it or not, what you've now done is come up with an expression for N2O2 using NO. So I can take this and sub in this up into here. Alright? Now what that means then, when I do that, I get rate equals K2 that I had before, times everything equal to N2O2, which is all this. I'm going to lump my rate constants together. I'm just going to make all these equal to K, because really that's all they are. They're just 3 rate constants. I'm going to make them equal to K. Times NO squared, and then I add in the O2 from the original reaction. So what that really means is, when I write this out again and I make all these 3 equal to this, the rate law looks like this. Rate equals K NO squared O2. Notice this rate law is exactly the same as this one. So when you ask yourself the question, is this a possible mechanism? First off, when you make sure that the 2 equations, when they add up, they give the overall reaction. If they do, then you go down and try this and see if you can get this rate law from the 2 rate laws you had here, and in this case we can. That tells us that this is right. Okay, and this process works whether you have a 2-step reaction, a 3-step reaction, a 5-step reaction. If the slow step is first, that actually makes the question a lot easier, because then the rate is only the rate law from that first step, and all the other fast ones come after it. Any fast steps you have before the slow step have to be taken into account in that reaction rate, if you understand. Because if this is the slow step, I have had to have gone through the fast one before I get here. So yes, it's true that this slow step is the one that determines the rate, but then this comes from here. So therefore, this NO has to be involved in that rate rate law as well, which is exactly what it is here. Okay. So remember, for elementary steps, you can write out the rate law from the balanced equation. For an overall reaction, you cannot do that. Okay. All right. So that's mechanisms and elementary steps. Thank you.